everybody. My name is John Harrigan. I work for Red Hat, and I work on a team called Performance and Scale Engineering. We focus on, as the name implies, to a certain amount of torture testing, new features, as well as trying to get a bit closer and expand testing activities within Red Hat beyond functionality into actual usability and into some what I would consider day two operations. So things beyond just looking at a capability from a raw performance standpoint. But as we move into some of the technologies, particularly in the software-defined storage area, I work with staff. It's a fairly complicated system. There's a number of background activities, and those can affect the quality of service at the client level. So I'm basically presenting today to talk about some of the tooling I've done, some of the tooling that is available out on GitHub for more thoroughly evaluating object storage with customer representative workloads. So I thought a little bit about as I was putting this presentation together, I thought a little bit about the takeaways and what kind of things I was trying to impart on attendees. And I came up with these 3 bullets here, trying to increase awareness and knowledge around designing the workload. When I say workload, as you see as we go through the slides, it's we in the performance and scale team, we not only look at a workload from a standpoint of a description of a specific benchmark exerciser, but we also look at it from the standpoint of how can we approximate some of the activities that happen at an operational level in a production environment. Then the next bullet talks about the specific storage workload tools that I've posted out on GitHub. And then finally some information about analyzing the results that come back from these runs and from these tools. So I'm going to start off by talking about the motivation, how you go about effectively designing workloads, the tools themselves, and then we'll have a demo and open it up for questions. The slide deck also does include some backup slides that have some additional detail on eye charts, particularly when it comes to analyzing the results. So on the topic of motivation to develop, there was basically driven out of initial customer experience with the Red Hat Ceph storage product, an identification of a need to start to incorporate workload-driven requirements into the overall development process, as well as the documentation aspects, test and release processes. And we also wanted to be able to effectively and efficiently reapply this test methodology in a continuous fashion through future releases. So we didn't look at this as a one-off exercise. So we knew that automating, and investing in some automation and knowledge transfer with other organizations would be time well spent. The premise behind this was to, as closely as possible, given our hardware footprints, simulate customer production environments. And by that I mean not do benchmarking, right? We were not looking to create publishable numbers here. What we're looking to do is identify deficiencies or issues within the product around unexpected changes in performance and unexpected increases, particularly in client latencies that would be found in production environments. We worked with a number of key customers to develop the workloads and then run those on scale-out footprints. And in addition to looking at the results that were coming back from the workload generator, we also wanted to capture things like system resource utilization statistics. So have an idea of what kind of memory and CPU were being used by the various Ceph processes and background services. So a few things here on this testing methodology slide, some of which may be redundant to the previous one. But the idea is to develop a comprehensive workload profile. And again, as closely as possible, simulate production environments. By that, right off the bat, pre-filling the clusters. So rather than running tests on brand new deployments with no capacity taken from pools, we run tests where we actually have specific activities around filling the cluster, aging the cluster, performing these kind of situations and applying events like failures to see how much the client performance is impacted. And the results of these tests have led to a steady progression of improvement in Ceph relative to the impact of these background services and the disruption to the client performance. So the workload generation that we use for this testing is an open source project that Intel sponsored called Koz Bench, and I dropped the URL in there. We chose that because it's fairly full-featured in terms of the statistics it gathers relative to the client experience, and also because it has a very rich definition language around workloads that allowed us to put together workloads that, again, come closer to simulating production environments. And I'll talk a little bit about more with that. So the topic of designing workloads, I tried to kind of break this up into a couple of different modeling areas. The first one for consideration is the layout, specifically the number of buckets or containers, as well as the number of objects per bucket. We were finding that a number of customers were actually using Ceph with extremely high numbers of objects per bucket and with unexpectedly small object sizes. So some of the performance testing that had been done previously left exposure points around some of the use cases that actually some of our largest customers were deploying with. The other thing around modeling, effectively modeling workloads, is the types of operations that are performed, and in particular, thinking about a mixture of operations rather than segmenting things off and testing them individually. We saw dramatically different reaction from the software-defined storage Ceph as we started turning knobs here, applying mixtures of operations and applying histograms of object sizes. And then the final point there is the throughput per day, mapping that back to something that's realistic in a production environment. And by that, I have a separation between what's being accessed and what's being modified, right? Which then in turn comes up with your operation mix. So let's talk a little bit about those final two considerations. First up, the sizing for capacity, which is one approach, and then the sizing for performance. So from a capacity standpoint, the metric we want to get to is thinking about the number of objects. And in this aspect, we're looking for the test conditions that are listed here in terms of available capacity, what's the desired % cluster fill, the object size, which again may or may not be a constant or a histogram, and then the number of buckets. This then gets us to a point where if we factor in the replication type, we can predetermine how full the cluster will be. For most of our testing, we run the clusters at least 30% full, and in most cases 50% full. And then the sizing for performance. This part of defining a workload, really, it needs to be done for you to identify a reasonable saturation point on the object storage itself. And the way we usually approach this is we have a target latency in terms of quality of service. And a lot of this is set by having discussions with customers around their production environments. And then what we're looking for is, extreme variations off of that latency. Working with Koz Bench, we size the cluster depending on the footprint and then the target latency, and we usually run a handful of these what I'll call sizing runs to determine that we're using the correct number of workers, or think of them as number of drivers from a workload generation standpoint. So I'd mentioned on an earlier slide about production, simulation versus micro benchmarks. And a fair amount of work has been done with Ceph, in addition to other storage systems, with what I would label as micro benchmarks. They tend to have a single operation type, typically, and most likely a single object size. And what we found with Ceph was that a fair amount of unexpected performance happened as you expanded beyond that kind of footprint. There's most definitely rules of thumb relative to object sizes and what kind of use cases those fit, which are listed on this slide. And then there are definitely operation types that are typically evaluated individually as opposed to in a mixed fashion. And again, those are listed here as well. And then the final point about a micro benchmark is, as a characteristic, it likely has a rather short duration time, a short run time. And it's run in kind of what I would consider a lab environment in terms of a freshly deployed cluster without any kind of expected interruptions from background services, or for that matter, any kind of infrastructure failures. This is what is frequently available for storage, and this is what frequently sets expectations and can lead to rather upset customers. Because as you bring in the reality of the production environments, you can see dramatically different results and some unexpected consequences. And that leads to identifying issues that need to be resolved in the implementation and the architecture, and that eventually leads to a more robust and more definable quality of service for your clients. So I've mentioned the production simulation. We directly took feedback from a couple of our key customers, and some of the more challenging ones I mentioned before were using Ceph with what we would consider to be extremely small object sizes. Here's one such example. Based on a 48-hour collection period, we saw 50% of the object sizes were at 1K. And we came up with a histogram here that we've stuck to quite a bit as we've done our release-to-release testing here, looking for regressions within Ceph. And you can see how that's laid out here in terms of small object sizes, then the 15% distribution amongst the 64K, 8 meg, and 64 meg, and then finally a small 5% footprint around the large object sizes. And that workload, the definition of the object sizes is on the top, the definition of the types and mixture of operations is on the bottom. So again, this was observed in a customer production environment and used as a baseline for a lot of our testing relative to identifying quality of service. Yes.
Do you use the same operation type and mix for each one of the object sizes?
So in Koz Bench, you're allowed to specify, literally give it a histogram of object sizes. And so that histogram is randomly applied to each of the operation types. Now, some of the operation types don't require in your workload specification an object size, right? If you're doing a list on a specific container with a specific bucket, with a specific object, you're not handing that operation an object size. But certainly with the rights you are.
From understanding your customer base, is the 60% read in a real world environment that's applicable to the 1K object as it is to a 1K object?
Yes. Yep. So when we do a pre-fill of the cluster, we use that object size histogram to lay it out.
I think the question was slightly different, right?
Okay.
The question is, when you collected the information from production monitoring for 48 hours,
Right.
and you observed the 60% read, was the 60% read equally distributed across all of those object sizes?
And the answer is yes. Yes. Yes.
That it isn't where you might have 1,000 tenants or
Sure.
100 tenants. And
Yeah.
each of them does a workload on a certain size object.
Yep. The tooling I'll show you gives you that flexibility to be able to put together workload specifications with that degree of specifics. Yep. Now, one topic I want to cover briefly here is around workload generators. As I mentioned, we're using Koz Bench. It's a Java-based application. It's separated into a client-server kind of model, or what's considered a controller, along with drivers. It supports multiple drivers. The drivers are fairly heavyweight Java processes that require fairly significant resources from your workload generation size. So you need to be aware of the driver processing overhead, and fortunately, Koz Bench provides something called the mock storage driver, which basically is equivalent to kind of like a dev null storage driver. So you can specify the actual delay period. By default, it's 10 milliseconds. I did some testing where I set that to 0. And my objective there was to try to understand how fast could I drive Koz Bench, or how fast and hard could Koz Bench drive infinitely quick storage, right? And the observations I came up with are listed here. So your biggest bottleneck from a Koz Bench throughput standpoint are write operations. And I eventually was able to look at this enough where I came up with an understanding of what I would consider, I use the word optimal here for ratio. Maybe it's better as a suggested ratio. But you really want to be careful about throwing too many drivers per hardware node and then getting very misleading results back from Koz Bench. So a rule of thumb here is to ensure that the workload generation side is not a bottleneck. And for Koz Bench, that ratio works out to be 4 drivers per client node. And each of those drivers themselves can, in parallel, support 3 worker threads. If you try to push too much further than that, you're going to be introducing some artificial delays from the workload generation size.
This is with dev null as the target device, or?
It avoids the communication to the storage device itself. So it's not exactly dev null. It's skipping quite a bit of code inside of the driver. Any of the code that's inside of Koz Bench specific to S3 or Swift or whatever is supported. So this is the driver processing overhead independent of having to touch storage.
And when you say 4 clients and 3 workers, I'm thinking 4 processes and then 3 threads, or
You literally, I'll show you how it's specified, but literally what you do is you tell Koz Bench, you configure Koz Bench for how many drivers you want it to be configured with, and on what systems those drivers should be running. So let's just go through some of the semantics of setting that up. This is another way of stating the system resource utilization on a per driver aspect. And you can run Koz Bench in any number of fashions relative to either starting with co-location of the controller and driver, or you can have one controller and have it communicating out to multiple drivers. And this provides basically the syntax of a key configuration file that's in Koz Bench called controller.conf. This example here shows if you were to have two drivers and they were both located on the local host, you list them out inside of this controller file, and you'll notice that the port offset is by 100. So when you use Koz Bench to basically say start driver.sh with two, it starts two separate driver processes and offsets the port count by 100. So you could do 3, 4, whatever in there. You need to manually edit the controller.conf so that the controller is aware of the IP addresses and the port numbers where each of those drivers reside. And then a quick visual of kind of a testbed configuration and components. In our configurations, we tend to use dedicated networks for the back end of the storage, which is at the bottom there, the Ceph cluster network. And then we have kind of the Ceph public network. And the Koz Bench workload generators are at the client level, driving workload into the Rados gateways, which are denoted with RGWs. So each of these nodes in the middle here are Ceph nodes.
The networking bandwidth on the tube?
We usually run with at least 10 gig Ethernet, more commonly 25 or 40.
Both or just?
Both. Yep.
How many racks and what's the rack thing?
So we have a scale lab that has, at this point, I think there's probably about 20 racks of equipment in there. Most of the testing we do at the scale is within one rack, if possible. Because it's a shared, the scale lab is a shared resource, so we don't run tests at the full footprint. Most of the tests that I would be doing would be probably involving between 12 and 16 storage nodes, each with 24 to 36 drives, be they NVMe or hard drives or a combination of both. So this is the inventory of the actual tools themselves and the URL out to the GitHub. The first tool is, it merely generates the workload files. So it's kind of a standalone tool that helps you generate workload files for Koz Bench. Generating workload files for Koz Bench can be a bit error prone or fat finger prone. It's XML syntax. So this is just a way of being able to specify the various characteristics of the workload and have it broken down into different work stages. And then there's RGW test, which is kind of the real workhorse. That runs the workloads and also does monitoring and captures logs with all of the system resource utilization. And it also has polling capabilities that can monitor things like garbage collection. And then the final two, I just put in there for people's knowledge. This software can run on Kubernetes, right? So there's a GitHub repo for that. And then there's a separate repo that focuses on injecting failures into Ceph OSD nodes and allows us to isolate recovery periods for whether the scenario is an individual disk or device going away as an OSD, or in some situations we take an entire OSD system offline and while we're applying a workload. So Gen XMLs, again, it's a very kind of simple and straightforward shell script. There's a series of template files for the XML workloads, and based on the variables and the way the variables are set inside the script, it creates the workload files for you. It also includes a handy utility, something called CB parser, which is a Python script that allows you to look at and produce Koz Bench reports outside of the Koz Bench controller GUI. So that's somewhat handy. So pretty straightforward usage. You edit the script. The key variables are listed here, right? The access key and the secret key and the endpoint. You give things a test name, so you have some way of identifying them afterwards, and then they're time-stamped. And then the key elements for the workload itself, the runtime, the object sizes, the number of containers, and the number of objects. And this produces the following workload files. But I mean, it's just very straightforward bash code that's easily modifiable if you wanted to create alternative workload files. But these create a sequence of workloads that we frequently use where we're doing the cluster prefill. Then we can run any of the, the sequential or random ops, which run in isolated mode as two separate work stages. But the workload that we use most frequently is called mixed ops, which performs this predefined mixture of operations that I mentioned before, all simultaneously. And then finally, there's an empty cluster that you typically run as the last workload. Now, I mentioned RGW test. This is the harness that will run the workloads. And it actually also has capabilities for generating workload files as well. But you can take workload files from Gen XMLs and run those here. The key thing that RGW test buys you is some additional logging over and above the results that Koz Bench provides. The monitoring that happens at the system resource level is all done inside of a polling script, and the frequency of that polling is user configurable. There's also heavily commented code around adding additional polling capabilities in there. So again, yes, question?
Does the test script always create a new poll?
When you run the reset script, it does, but you don't have to necessarily do that. And in fact, we try to resist doing that because we're trying to simulate production environments, so we want certain aging aspects to come through. A usage step here in terms of write XML, which produces the XML files for RGW tests, reset RGW, which is what recreates the pools, and then a series of these run IO workloads where you go through the scenario of pre-filling, aging, and measuring the cluster performance. So these are the three workload files that RGW test produces, but again, you can pull in workloads that were created with the Gen XML tooling as well. I have two slides here that talk about the key variables relative to RGW test configuration. Since it reaches out to the Ceph systems to identify system resource utilization, it needs to know their system names, right? So there's a MON host name, an RGW host name. It needs to know where Koz Bench has been installed because it issues the command to start the workload to Koz Bench itself. And then there's authentication information in there, endpoint information, whether you're using three-way replication or some form of erasure coding. And then there's, for Ceph purposes, there's PG-num information that's applied to the pools as they're created. And the second set of key variables here having to do with the workload definition, things like object sizes, number of containers, number of objects, etc. And then I spoke before about sizing up the cluster for identifying a performance threshold, and that's where these worker counts come in. There's support for individually specifying the number of workers that you want to be used for the cluster fill versus the actual measurement workload. I just wanted a quick slide in here to let people know that this is extendable. So while it supports certain workloads based on pre-existing templates, you can define new workload specifications by either modifying existing templates or creating new ones. So let's take a quick look at a log file. I mentioned that RGW test squirrels away system resource information by polling periodically in a background process. And by default, it collects those statistics on a 1-minute interval. And the types of things it grabs are listed here. And all of the entries are time-stamped. So as an example excerpt from a log file run, this would be something where we would be looking at the start and the end, and specifically the information that was parsed out from the results of running CephDF. Now, this testing harness was used to do a performance evaluation a while back on the transition from file store to BlueStore support within Ceph. And this table here shows the performance advantage that was measured using this workload approach for BlueStore. So in addition to the Koz Bench results, which are seen in the table up above, the log file statistics provided a deeper level of insight because they recorded things like load average as well as CPU usage for the various Ceph processes. Here's a view of what we call the hybrid workload. So the previous one was for cluster fill. This is for the mixture of operations. And again, you can see the percent change with BlueStore. And again, the log file statistics. So let's see how I do on time here. I'll put the spectacles on. All right, so what I've got running on my laptop is a containerized version of Ceph with a fairly small footprint. And what I thought I would do is real quickly just generate some workload files and then run them through the scripting. So I've got a collection of, so this is the repo from GenXMLs, and you can see the CB parser script there as well as genxml.sh. So that then created these workload files that we see here, preceded with test 1. So if we just wanted to take a look at the fill workload, Again, all the script does is reach into the XML templates, which has a template file for each of these types of workloads, and it fills it in with information that came out of the shell script. So it's got the access key and the secret key and, all the authentication information in there. And in this case, we're running on the laptop, so we're keeping things pretty small. We've got, 2 workers specified, and then using a total of 5 buckets, each with 500 objects and at a constant object size for demo purposes. So let me bring up. This is the Koz Bench aspect of the demo that's running, and for those who haven't seen it, there's a CLI way to submit the workloads, but there's also a way to do that through this GUI, this controller GUI. So if we press submit here, this should take about a minute to run this particular workload. This controller GUI in Koz Bench does show you what's called a performance graph that just refreshed here as the, and it shows that in terms of throughput as well as response time and bandwidth. All of the information that Koz Bench is collecting here, it puts it in an archive directory, and so we can use that CB parser Python script to basically get a textual version of this after the run is over. Let's see, I think I put it up here. Yeah. And this would be in the archive directory, and should be all right. So that job completed, and if we go back to the index, we'll see that listed in our inventory now as W1, and we can see that, again, just this Python script just goes through that archive information and creates something that Koz Bench is called the general report. It shows information about average response time and processing time, throughput. And then we frequently look not only at average response time, but we also pay very close attention to things like 99th percentile response time to make sure that there aren't dramatic spikes in some of the higher latency counts.
John,
Yeah,
the GUI that you showed, is it part of the Koz Bench?
correct.
Okay.
Yep, yep. And if we go over to, right, so let me go. So I have this little shell script that just basically does a S3 command output and then does a cefdf. So we can see that the cluster fill did hit, use up some amount of the storage on the containerized Ceph. If we take a look at RGW test, so what we see here is that there's several what are called results directories. These are time-stamped. The utils directory contains the probe or polling. So there's a script in there called poll.sh, which is what grabs the various Ceph statistics. And then there's the run IO workload.sh, which is what actually issues the job. So we can go and run. Let's run an empty. So I'm going to reuse the the workloads that were created in that GenXML's directory here. And so this is the syntax that you can hand to run IO workload. And as this runs, it'll do some monitoring in the background. So everything you see going across the screen right now is going into a results file that's time-stamped with the job ID associated. And we can see here some of the information that's being captured by the polling, right? It's got the % raw used, it's got information about memory footprint as well as processor activity going on for the various Ceph processes. And when this wraps up, it'll tell us the name of the log file that captured all the results here. So we frequently do runs that may run for days, right, in order to simulate aging. And a lot of what we're looking for is, okay, let's take a fresh deployment. Let's do what we consider a measurement run to get a feel for what the performance is. Then we'll do some amount of aging, and that may include, an infrastructure failure. Or, in addition to just running workloads for an extended period, there may be other operations that are injected into the cluster. And then we'll rerun a measurement run, which typically we run for about an hour or two, looking for any significant deltas off of what we started with as an initial installation to help identify expectations around degradation as the cluster ages. And this analysis and work has I think, as I mentioned earlier, has led to a number of improvements, particularly in RGW garbage collection and some of the efficiencies for some of the Ceph background services that have to do with operational events. So at this point, that completed, you can see the name of the log file there listed. And you can also see, if we go back up and refresh this Koz Bench GUI, right, we can see that there's now been a fill load run as well as an empty load. And if we go in, the statistics are provided there within that GUI, but they could also be seen using that CB parser utility as well. So that's about it. Questions?
The output files we were looking at seem targeted towards human readable. Do you have something else that goes behind and pulls them into Canvas data frames or something interesting to make them more easily analyzable?
Yeah, so we typically do things with Prometheus and Grafana. But that whole infrastructure isn't integrated into what's on GitHub, right? But it could certainly be adapted for that.
Then one other question. When you went through the customer view of their data set and what they have, I don't know if Koz Bench can do it or not, but there was no mention of the compressibility or dedupability of the data set.
Yeah, actually, it's something I've started working with recently. By default, Koz Bench supports two streams of what I would consider prefill for the objects. By default, it uses, this is set with a flag called content equals. By default, content equals what Koz Bench considers to be randomized. But if you really look carefully at the code, what you find out is that it's a repeatable randomized pattern. And it's only generated from a small subset. It's generated from the lowercase characters of A through Z. So that's been extended by the storage provider Nexanta. They have a GitHub repo with a version of Koz Bench that does truly randomized input with non-repeatable chunks. And so we've been starting to utilize that now as we're taking closer looks at dedupe and compression. Yes?
That's a good segue to the concern I have. So the Koz Bench that is with Intel, it seems like it hasn't been updated.
Yes, yeah.
I even tried to contact the the contributors and
Yeah.
so is there an industry-wide kind of consensus on maybe have a official fork of it that then people start following?
Yeah, I wish there were. A number of people have taken it in different directions. Like I mentioned, the next unfortunately, there's no single place where all of this is being rolled up. So it is stale. I've worked through the specifics of how to rebuild it, and that takes a fair amount of heavy lifting. And it's something that I plan to put out on GitHub, basically the steps that I was successful with. There was one fellow who basically submitted a series of pull requests specific to the latest release, which is 0.4.2, which out of the box will not work, right? And it will not build. So he submitted a series of pull requests to get that to the point where you could build it, and I verified certainly that is correct, but you have to go to several different places to get the information in order to rebuild this. So I put together a brief not so brief document that talks about using those pull requests as well as how to rebuild it, with success using the 0.4.2 code base. So that's something I'll be putting up on GitHub as well.
Yeah, because performance is the sensitive topic when it's published in a white paper or whatever, and if you can't even agree on the tool that generated those maps or whatever,
right,
versus which branch, and so.
Yep. Any other questions? All right, thank you.